Okay, in the first part of our revision, we are going to look at energetics and particularly the application of the Hess cycle in order to calculate the relevant enthalpy changes. Some of you might be wondering why is there a need to draw the Hess cycle and what exactly is useful about linking up the different energetics terms. So I will just use a very simple examples to highlight to you. You would have read that particular examples or encountered that particular examples in your lectures. So let this serve to be some form of a revision. Okay, so the first thing we are looking at is probably the definition of the enthalpy change of formation. Yeah, so in the course of your studies for energetics, it is very important for you to be very clear of all the energetics terms which we are dealing with. Okay, so that will be the last page of your lecture notes where we ask you to write out the definition for the various terms. So let it be serve as a good summary for you. But of course, each of the terms have their physical meaning. That means that you have to be familiar with them as well instead of just memorizing them blindly. Okay, so first of all, I will attempt to go through a very familiar examples with you, which is the enthalpy change of formation. So in this case, we are looking at the enthalpy change of formation of natural gas, otherwise known as methane. Okay, so you notice that the definition of enthalpy change of formation, in this case for methane, it states that it's the enthalpy change when 1 mole of methane is formed from its constituent elements. The constituent elements of methane will be carbon and hydrogen, and because it's standard enthalpy change, so we are looking at the standard states of carbon and hydrogen, which will be solid and gas respectively. Okay, so this will be the enthalpy change of formation of methane. It is difficult, or it is almost impossible experimentally to determine a value for the enthalpy change of formation for methane in this case. Yeah, so if I were to put carbon and hydrogen gas together, right, no way will they react to give you methane gas. So in that case, I have to determine the value for the enthalpy change of formation for methane in a different way. Okay, so we probably want to be able to connect them through a cycle, and that's how scientists came up with the Hess cycles. Okay, so in this case, I will illustrate it using the examples of combustion. Okay, so if we are going to burn natural gas, in this case methane, okay, I'm going to write it below here. We're going to end up with CO2, carbon dioxide, okay, plus H2O. Okay, so when we try to link up this portion, right, there is an extra elements component, which is the oxygen gas. So we need to sum up the total number of moles of oxygen. So in this case, there are 4 oxygens in total, so we need 2 moles of oxygen gas. Okay, so you notice that if I'm going to introduce oxygen on the right hand side of the equation, I also need to introduce it on the left hand side of the equation because of the conservation of mass here. Okay, so we cannot ignore the contribution of oxygen on both sides. Okay, so remember that mass balance is a very important aspect for the balancing of a Hess cycle. Okay, so once we introduce the oxygen on the left, you realize that what we are defining in the arrow downwards from the left would be the enthalpy change of combustion of carbon. So this will be enthalpy change of combustion of solid carbons. Okay, and the enthalpy change of combustion of hydrogen gas. Okay, but because there are 2 moles of it, so we need to multiply this value by 2. Okay, and of course from the right arrow downwards, that would be the enthalpy change of combustion of natural gas. Okay, so from the above, in order to calculate the enthalpy change of formation, we will need to take an alternative route, in this case anti-clockwise manner. So when we are taking an alternative route, we need to track the direction of the arrows. So if it's in the same direction of the arrows, then we'll just let it be. So that will be enthalpy change of combustion of carbon plus the enthalpy change of combustion of hydrogen gas times 2. If it's against the flow of the arrow, then we need to minus it. So that will be minus enthalpy change of combustion of methane. Okay, so if we know the values to this, and this, we will be able to obtain a numerical answer for the enthalpy change of enthalpy change of formation of methane. Okay, so this is how we go about drawing the Hess cycle in a nutshell, and why do we need to draw the Hess cycle. Okay, so we will now move on to question 1. So for question 1, it reads, the equation below shows how PCl5 reacts with limited amounts of water, and you are given the following data. Okay, so what we're going to do now is, based on the data, come up with a Hess cycle. Okay, now you notice that the data given to you are all enthalpy change of formation of the respective compounds. In this case, PCl5, POCl3, and HCl. You notice what's missing is the enthalpy change of formation of water. That is missing. But it is okay because we are given the enthalpy change of combustion of hydrogen gas. Yeah, so if you are going to write out a definition for the enthalpy change of combustion for hydrogen gas, it will be H2 gas plus half O2 gas, and you're going to end up with H2O liquids. Yes, so essentially the enthalpy change of combustion for hydrogen gas is the same as the enthalpy change of formation of liquid water. Yeah, so in this case you have to recognize that they are the same. Okay, so once you recognize it, then it will be quite straightforward to come up with a cycle. So I will probably start on the right hand side. So for POCl3, what I'm going to have here will be a quarter P4 solids plus half O2 gas plus 3/2 Cl2 gas. Okay, and this is going to take the value of negative 1186 kilojoules per mole. Okay, and then I'm going to use a different color. Okay, I'm going to use blue. I'm going to define the enthalpy change of formation of HCl. In this case, 2 moles of HCl. So I'm going to write it below. That would be H2 gas plus Cl2 gas. Okay, so I'm going to just use the same arrow, although technically the arrow should be like this. Okay, sorry for the weird looking arrows, but yeah, you know what I'm trying to say. So this value will take on negative 92 multiplied by 2, because enthalpy change of formation of 1 mole of HCl gives out 92 kilojoules of energy. So 2 moles of HCl, you will give out double the amount of energy. Okay, and next, you would expect the equation to balance from the left downwards. The reason is, if I can balance this particular portion, right, then I would expect this particular portion to be balanced as well. So if you don't believe, let's try. Okay, so I'm going to just highlight the total amount of Cl2 I have. So we have 3/2 Cl2 and then 1 mole of Cl2. That's a total of 5/2 Cl2, which matches this. Okay, and of course, I have a quarter P4, which essentially is P. So over here, I will be able to define the enthalpy change of formation of PCl5 safely. So that will be negative 4, 4, 4. And then earlier on, we talked about the enthalpy change of combustion of H2. So in this case, we have the exact ingredients here. So that's half O2 and H2. So in this case, if I'm going to write it in, it will be negative 286. Okay, yeah. And our final check would be to ensure that whatever I have circled, okay, so maybe I'll circle it again. So just ensure that there's material balance over here. There is also material balance over here and as well as material balance here. So it is only when the material is balanced on all sides that you know that you are on the right track. If you are more experienced, actually you do not need to keep checking, because you will check as you do, but just ensure that you are on the right track in the very beginning stage of learning and also for revision. Then I think it will be good to check. Okay, so again, how are we going to sum everything up? So again, we're going to do an anti-clockwise from left to right. So if you are in the same direction of the arrows, you just keep the sign. Opposite direction, just reverse the sign. Okay, so the enthalpy change of reaction here is therefore equals to 444 plus 286 minus 1186 and minus 92 times 2. Okay, so once I sum up everything, I'm going to end up with negative 640 kilojoules per mole. Okay, so take a bit of time to check through your answers and make sure that you are able to sum them up in the appropriate manner, because this is the fundamentals of how you should be working on questions like this. Okay. Next, we'll move on to question 2. Okay, you should have tried them out on your own. If not, you should pause the video for a while. Okay, so for question 2, we're going to do the same thing. You are given an equation showing the iodination of methane. So it's a mono iodination of methane. Okay, so we have CH4 gas plus I2 gas, and in the process, you end up with CH3I plus HI gas. Okay, so we'll do the same, we'll go through the same thought process. So in this case, let us look at the enthalpy change of formation of HI and CH3I first. Okay, so for the enthalpy change of formation of CH3I, we are looking at carbon solids plus 3 H2 gas plus half I2 solids. Okay, some of you might be asking, why is it solids? But remember that the enthalpy change of formation, the definition is that the formation of one mole of the compound from its constituent elements in the standard state. So the standard state of iodine is solid. Okay, right? Maybe I should color code this so that it might be a bit easier for you to follow. Okay, so I will just write in red. Okay, so plus 2HI. Okay, so in red here, oh sorry, not 2HI, just HI. Okay, so in red here, I'm going to write out the definition for the enthalpy change of formation of HI. So that will be half H2 gas plus half I2 solid. So you notice that standard condition is still solid. Okay, so nothing has changed. Okay, so I'm just going to write the arrows here. Okay, so I'm just going to park the values in. So for HI, that will be 26.5 kilojoules per mole. For CH3I, it will be 14.4 kilojoules per mole. Okay, both are endothermic. Okay, then from here, you will recognize that if I'm going from right to left, okay, I will be able to define the enthalpy change of formation of CH4. Okay, CH4 over here, because I have the constituent element which is carbon solid, and then I have the constituent elements of hydrogen in its standard state, which is dihydrogen gaseous. Okay, and this value will be negative 74.6 kilojoules per mole. Okay, and of course, the elements over here will just get carried over. So I'm just going to write it in yellow. So plus I2 solids. Okay, then finally, I'm going to sublime the iodine. So that will need 62.4 kilojoules per mole of energy. Okay, so there's a slight typo here. You might just want to correct it. This should be per mole. Okay, so we're supposed to calculate delta HR. So we're going to do the same thing anti-clockwise like this. Okay, so in this case, delta HR is equals to negative 62.4 plus 74.6 plus 14.4 plus 26.5. So I'm going to end up with plus 53.1 kilojoules per mole. Okay, yeah, so after you work on it for some times, you realize that it's pretty straightforward. It's not as difficult or as daunting as it seems. Okay, we'll move on to question 3. Okay, so for question 3, you are given liquid PCl3 is prepared by the reaction of chlorine with white phosphorus. So you are given some related thermochemical data here. Okay, so I will just write out the definition for the enthalpy change of formation of PCl3. So this will be PCl3 liquids. Okay, so the standard state of phosphorus is actually P4, in this case white phosphorus. So I will have a quarter. Okay, P4. Okay, solids plus 3/2 Cl2 gas. Okay, so over here we are defining the enthalpy change of formation of PCl3. So this will be negative 320 over here. Okay, then the next thing we are going to look at will be the vaporization of PCl3, because at the end of the day, if you look at the nature of the question, we are supposed to construct an energy cycle to determine the PCl bond energy in PCl3. So in order to determine the PCl bond energy, as you know the definition for bond energy, the unknown, in this case the compound, has to be in the gaseous phase. Okay, so in that case we have to vaporize PCl3 to the gaseous phase. So in this case, when I vaporize it, I will need 32 kilojoules per mole of PCl3. So in this case, I'll get PCl3 gaseous. Okay, and then what I'm going to do now is I'm going to define, or rather I'm going to atomize my phosphorus as well as Cl2. Okay, the reason is once I subject PCl3 to the relevant bond energy, so in this case 3 multiplied by Be of PCl, okay, what I'm going to end up with will be the relevant gaseous atoms. In this case, 1 mole of phosphorus gaseous atoms and 3 chlorine gaseous atoms. Okay, and then now I'm going to complete the loop. So first of all, I'm going to atomize phosphorus. So for every 1 mole of gaseous phosphorus form, gaseous phosphorus atoms form, I will need 314 kilojoules of energy. So this will be 314. Okay, then for Cl2 over here, because I'm forming 3Cl, so in that case I'm breaking 3/2 of the Cl-Cl covalent bond, so that's 3/2 times 244. Okay, so again, I'm going to, okay, so this is slightly different. So because I'm going in this direction, okay, so therefore I'm going in a anti-clockwise fashion like this. Okay, so therefore 3 times Born energy of PCL is actually equals to negative 32, positive 320, 314 plus 3 half times 244. Okay, so if you quickly use your calculators to sum them up, let me just use the calculator. So I get 32 plus 320 plus 314 plus 244 plus times 1.5. Okay, so I'm going to end up with 968 over here, and then I just divide by 3, so I should end up with around 323 kilojoules per mole. Okay, so so that is 3 BE of PCL. Okay, so the Born energy of PCL will then be divided by 3, so I'm going to end up with 323 kilojoules per mole. Okay, now you notice in some of your exam, right, when you calculate Born energy, you end up with a negative number. That is totally incorrect, because Born energy can only be endothermic by definition. Alright. Okay, we'll move on to the next topic on the Born-Haber cycle. Okay, for the Born-Haber cycle, a very generic cycle is being drawn here. But remember that this is just trying to showcase to you the thought process. Okay, so never should you in an examination setting, right, combine IE and electron affinity together. Okay, so maybe I should write in red. So in an exam setting, do not combine them. Do not combine IE and EA. Yeah, this is just meant to be like a summary for you to see the flow. Okay, and of course, most importantly, you need to have a 0 point, which is your elements, and that is where you define the enthalpy change of formation. Okay, so we're going to use, or rather I'm going to use question 1 to illustrate to you how this can be done. Okay, so in this case, your job is to draw a Born-Haber cycle to calculate the lattice energy for magnesium fluoride. Okay, so of course the first thing I need to do is to write out the vertical axis, so that's energy in terms of kilojoules per mole. Okay, and then remember earlier on what we need to define the 0 point, right? So we're going to have 0 here. Okay, so this will be magnesium solids plus F2 gaseous. Okay, so over here I'm going to define the enthalpy change of formation of MgF2, magnesium fluoride. Okay, so I'm going to search for the values. Is negative 1121, so that's negative 1121. Okay, now I often find it easier to define the lattice energy after this. Yeah, so the reason why I find it easier is because it's easier for me to look at how things flow going from the native element to the gaseous ions. So over here I'm going to define the lattice energy, so that's Mg2 plus gaseous plus 2F minus gaseous. Okay, so this will be the lattice energy which we are required to calculate. Okay, now for the rest of the enthalpy term, we're just going to go up, up, and then eventually we'll go down a little bit. The reason why we go up and up, it's because we are introducing energy. Number 1, to atomize the relevant elements. Number 2, we need to eject out electrons from the gaseous metal atom. And then after that, the final exothermic term is because of the electron affinity, which I think over here you can see that it's actually negative 328 kilojoules per mole. Okay, so with this particular understanding in mind, let us just try to link up everything. So first, I'm going to perform the enthalpy change of atomization for magnesium. So that's 148. Okay, so I'm going to end up with magnesium gaseous plus F2 gaseous. Okay, and then after that, I'm going to atomize fluorine. Okay, but atomization for fluorine is not given to us, but we can go to the data booklets to find its Born energy. Okay, because 2 times enthalpy change of formation, 2 times enthalpy change of atomization of fluorine is equals to the Born energy. Okay, if you are unsure why is that the case, it can easily be done. Because by definition, atomization enthalpy for elements look at the number of moles of gaseous atoms formed. So in this case, atomization for fluorine is defined as half F2, okay, to give you 1 mole of gaseous fluorine atom. Okay, but however, for Born energy, we are looking at introducing a fixed amount of Born energy in order to break the FF covalent bond. So we end up with 2 moles of fluorine gaseous atoms. So you realize that this equation and this equation essentially is the first one is the second one multiplied by 2. Okay, so we can easily do that. Just flip over to the data booklet. We will see that the value is actually 158 kilojoules. And then after that, I will end up with Mg gaseous plus 2F gaseous. Okay, then finally, I'm going to introduce ionization energy. So for ionization energy, I'm going to do the first 2 IEs together. So that will be 736 and 1450. Okay, so I will end up with Mg2 plus gaseous plus 2 electrons plus 2F gaseous. Okay, I will complete the rest by moving down. So maybe I should extend the line a little bit. Okay, then I will move down, and in that case, I'll be defining the electron affinity of fluorine. But remember, you need to multiply by 2 because you are forming 2 moles of fluoride gaseous ions. Okay, then let us try to use Hess law to sum up everything. So lattice energy is defined from the gaseous constituent gaseous ions to the ionic compound. So this will be the starting points, and this will be the ending points. Okay, so in that case, in order to sum up, we need to move in this direction. This will be an anti-clockwise direction like this, all the way down. Okay, so you realize that when you move in this particular direction, you can sum them up and get the values for the lattice energy directly. So lattice energy is therefore equals to 328 multiplied by 2 minus 736 minus 1450 minus 158 minus 148 minus 1121. Okay, so if you punch your calculator, you should end up with negative 2957 kilojoules per mole. Okay, as I often tell my students, all road leads to Rome. This is not the only way you can sum up. Okay, maybe during your tutorial lesson, your teacher might have told you that, okay, what you can do is you define the enthalpy change of formation. So that will be minus 1121, and then after that you sum everything up like this. Okay, yes, you can do that if you want. So, but you end up with the same answer. So that will be negative 1121 equals to 148 plus 158 plus 736 plus 1450 minus 328 times 2 plus lattice energy. Okay, but when you do that, you still need to shift. This whole portion to the left hand side before you calculate. Yeah, but if you just look at the destination, at the starting point and destination directly, you can just sum them up directly. But you just need to be a bit careful with the sign. Okay, so if everything's good, we'll move on to question 2. So for question 2, we are working on the the construction of a Born-Haber cycle for the formation of solid iron sulfides from its elements. But in this case, we are not calculating the lattice energy because it's given to us. So we are supposed to calculate the second electron affinity of sulfur. Okay, so with this, we'll work on it using the same thought process. Okay, so first we have the energy axis in terms of kilojoules per mole, and then we just write it out vertically. Okay, and then again, it's the same thing. We'll I think earlier on, remember the 0 points, so we'll do the same thing. Remember to introduce the 0. Okay, the 0 points, and then in this case, we have iron, solid, plus a quarter, S8. Oh, sorry, actually it's not a quarter, it's just 1/8 S8 solids. And in this case, you'll end up with iron sulfide solids. Okay, so this is the enthalpy change of formation, which if you look up here is -101. Okay, so using the same thought process I mentioned earlier on, what you need to do, or what I will do, is now I will be defining the lattice energy, which is given to me to be -3556 kilojoules per mole. So I'm going to write it as Fe2 plus gaseous plus S2 minus gaseous. Okay, then again, same thing. I'm just going to go up and then down. Okay, but of course in this case, we are going to have first electron affinity of sulfur and second electron affinity of sulfur. So it's a little bit different, but the bulk of the gist of the idea is the same. Okay, so we're just going to use the data. So we're going to atomize iron. Okay, so I'm going to get iron gaseous plus 1/8 S8 solids. When we atomize iron, this is 414. And then next we're going to atomize sulfur. That's 279. Okay, so we're going to get Fe gaseous plus S gaseous. Yeah, you realize that when you do energetics, right? When you work on energetics problems, you need to be systematic when you're drawing the cycle. Yeah, to be systematic is the most important aspect. Okay, and then after that, I'm going to introduce first ionization and second ionization energy of iron. So a quick check on the data booklet, you get 762 and 1560. Okay, so I'm going to end up with iron 2 plus gaseous plus 2 electrons plus S gaseous. Okay, and you notice that the first electron affinity of sulfur is exothermic. So in this case, your arrow must point down. So that will be -200. So when you point down, you need to be a bit careful. So Fe2 plus gaseous plus electrons plus S minus gaseous. And then the final bits, you need to point up, and then you just let it be your unknown. So let's just call it A. Okay? Yeah. So same thing. So this is your destination. So this is a starting point. You can choose to do that if you want. If not, then we can try to do what we mentioned earlier on, to start off from the elements to the product by defining the enthalpy change of formation. That is fine as well. So really, all road leads to Rome. Really up to you how you want to go about working on the problems. Okay, some of you might be wondering, why am I so sure that the second electron affinity is endo? Yeah, because based on what you learned in lectures, to define the second electron affinity, right, that will mean that I need to force electrons into an anion that is already negatively charged. And that is not so simple, because it involves some form of electrostatic repulsion. Yeah, so I mean, that's just a very simplistic explanation. So with that, in most cases, you would expect the second electron affinity to be endothermic. Okay, so with that ideas, I hope you can understand why I point my arrows up. Okay, so in this case, we try to define the enthalpy change of formation. So we have negative 101 equals to 414 plus 279 plus 762 plus 1560 minus 200, okay, plus A minus 3556. Okay, so with this, we will solve for A. We should be able to get 640 kilojoules per mole. Okay, so this will be the second ionization energy of sulfur. Okay, if this is okay, we'll move on to question 3, which again is not something which is very complicated. It's also probably something which, after you are familiar with question 2, is not a mountain too tall to climb. Okay, so yeah, we'll just do this really quickly. So all the standard stuff. So energy in terms of kilojoules per mole. Okay, so we're just going to write everything out. Oops. Okay, so let us try to see what are we supposed to do. Oh, we're supposed to calculate lattice energy. So again, we are on familiar grounds. So again, we define the 0 points, 2 Al solids plus 3 half oxygen. Okay, so here we are defining the enthalpy change of formation of Al2O3. So if we check above, is negative 1676. Okay, so that will be Al2O3 solids. Okay, then remember earlier on I was sharing that I will always like to define lattice energy. So lattice energy will be somewhere here. So this will be Le, the lattice energy for Al2O3. So this will be Al3 plus gaseous plus 3O2 minus gaseous. Take note of the coefficients, because that will actually tell you that you need to multiply by some factors. Okay, multiply by the relevant stoichiometric coefficient. Okay, so once we are okay, we'll just move up. Okay, so we're going to atomize aluminium, and we're going to atomize oxygen as well. Okay, so aluminium atomization is 326. We need to multiply by 2. Okay, so we're going to end up with 2 Al gaseous plus 3 half oxygen. Okay, then after that we're going to atomize oxygen. So bond energy of oxygen double bond is 496. So we'll take 3 half times 496. So we're going to end up with 2 Al gaseous plus 3O gaseous. Okay, then moving on, we're going to introduce first IE. Now, first IE, second IE, and third IE. Now, this is going to be a little tricky, but I'm going to write out the outcome first. So Al3 plus gaseous, 2 of it, plus 6 electrons, plus 3O gaseous. Okay, why is it tricky? Because we have first, second, and third IE. So make sure that when you sum them up, you sum them up properly. So that will be 577 times 2. So that's first IE. And then 1820 times 2. That is second IE. And then 2740 times 2. That's third IE. Okay, and notice that we are given the enthalpy change of electron affinity of oxygen here. Yeah, so with that, so we're going to try to link them up. I know that the length of the arrow doesn't really match the values, but it doesn't really matter, because at the end of the day, we will still be able to end up with the correct computation if we punch our calculators correctly. Okay, so we're going to go down negative 141 times 3. Then over here, we're going to end up with 2Al3 plus gaseous plus 3 electrons plus 3O minus gaseous. Okay, then we're going to go up. Okay, and this is the second electron affinity, so that will be 8, 4, 4 times 3. Okay, so in that case, we're going to do the same thing. Lattice energy, we're going to go down, go up, and then all the way down. Okay, you can punch your calculator and see if you can end up with the same answer as me. So that lattice energy is therefore equals to negative 844 times 3. Okay, plus 141 times 3. Then negative 577 times 2, negative 1820 times 2, negative 2740 times 2, negative 3 half 496, negative 326 times 2, and then negative 1676. Okay, so our lattice energy eventually will be, if you punch the calculator, it will be negative 15,455 kilojoules per mole. So if we leave it as 3SF, that will be negative 1.55 times 10 to the power of 4 kilojoules per mole of energy. Okay, take note that I think my writing here is a bit messy. Yeah, but I hope it didn't give you that wrong impression. So this is 326 times 2 minus 1676. Okay, yep. Okay, so with this, we have come to the end of the energetics revision for the November study program. Yep, next we're going to move on to kinetics. Okay, the next section we are going to look at would be reaction kinetics. Okay, you should have done some basic revision from your lecture notes, and if you run into any trouble, it will be good to revisit some of the lecture exercises as well as your tutorial problems. So for this study program, we are just going to focus on the basics in terms of identifying the order of reaction and as well as looking at the basic shape of the graph. So the basic shape of the graph could be zero order, first order, or second order. Okay, so I think first of all, we need to be we need to go back to the basic. For example, if we have a reaction involving A and B, which in this case give us the product. So let's say we don't know the order of reaction with respect to A or B. What could we do in a so-called an experiment to determine the order? Okay, so there are actually several ways which you can go on and carry out the experiment, but I'm just going to share with you what we will normally do, which makes perfect chemical sense, and this is probably what you need to know for at the H2 level. Okay, so normally you would have seen, for example, you don't know the order of reaction, so you have written the rate law in this fashion. So in this case, the rate law is K, and then concentration of A raised to the power of M, so that's nth order, and then concentration of B raised to the power of nth. Yeah, so it's nth order respect to B, nth order respect to A. Yeah. In order to determine the value of M and N, usually we will conduct an experiment where one of the reactant is in excess. Yeah. So for example, so maybe in one series of experiments, so let's say for the first series of experiments, yeah, what you can do is you will use A in much greater excess than B. Yeah. So in this case, you are able to write out a new rate law where rate is equals to K prime concentration of B to the power of N, where K prime is equals to K A raised to the power of M. Why is that the case? You might be wondering. Okay, the reason why this is possible is because, right, when the concentration of A is much greater than B, the change in the concentration of A would be negligible in the course of the reaction. So even if M takes on some values, it will be assumed that it will not drastically affect the rate of the reaction. The reason is the amount of A which gets consumed is a relatively small amount as compared to the overall concentration of A. Yeah, so this is a pretty ingenious way of designing experiment, and it has been done pretty much in the early 20th century, even the late 19th century as well. Okay, so once you plan the experiment in this way, right, we will call this thing a pseudo nth order reaction. This is known as a pseudo nth order reaction. In this case, of course, nth order respect to B. Yeah. So you will, in that case, you will design an experiment where you will, along the course of the experiment, try to monitor the concentration of B in whatever means you have learned. For example, it could be colorimetry, or you could quench it and then you perform a titration. Maybe because B could be acidic or B could be alkaline, or in whatever way that you deem suitable. Yeah, and then from there you can determine what is the value of N. Yeah, so this will be the first series of experiment which you can carry out. And then after that, what you could do is you could repeat this, in this case by making B in huge excess and then making A the limiting, or you could simply just double the concentration of A, and then you compare between the first series of experiments and the second series of experiments. Okay, so when you so for example, the concentration of B could be say 0.1 moles per dm cube. The concentration of A could be 1 mole per dm cube, and then when we double the concentration of A from 1 to 2, despite being the constant here, but because the bulk concentration is now doubled, yeah, you can check whether it will affect the overall rates of the reaction. And then from the way the rate is being changed, you can then, or it's being different, you can then determine the order respect to A as well. Yeah, so I'm just running you through a very brief view on the basic mathematics involved and the basic thought process in determining the order of reaction. So any of the details which you need, I think you should go back to your notes and notes down on those fundamental aspects. Okay, so in this case, I will not attempt to go through everything here. For example, getting the units of the rate constant, it's not something which it's very difficult. All you need to do is just to make sure that your units on both sides must be the same, and then you just cancel them off accordingly. Okay, and you would have gone through the pre-lecture exercises as well. Okay, and then of course the other aspect will be the graph sketching. So I think over here we will discuss the graph sketching a little bit. Okay, so now we are looking at the rate of this particular reaction involving oxygen and NO. So you can see that the rate law is first order with respect to oxygen and second order with respect to NO. So you'll notice that they also follow the same thought process. So in this case, NO is in excess. Okay, so NO is considered to be constant. So now we are getting a pseudo second order reaction with respect to NO. Pseudo first order reaction with respect to O2. So that's over here. So what am I talking about earlier on? Yeah, so this is over here. And then for the other side will be pseudo second order respect to NO. Okay, so because it's pseudo first order, and one of the most important graph sketch you need to be familiar with is rate against concentration. Yeah, so you know that for first order kinetics, the rate of the reaction is directly proportional to the concentration of the reactants. So in this case, you would expect a straight line that passes through the origin. Okay, so let me sketch the straight line in a nicer way. Okay, so a straight line which passes through the origin. Okay, and then next we look at a second order reaction. So a second order reaction means that when the concentration of NO doubles, the rate will quadruples. Yeah, so it will always be raised to the power of 2. And then using simple mathematics, because it's raised to the power of 2, so you expect the graph to curve upwards. Okay, well, depending on the values, of course, it could curve earlier or later, depending on the value of NO. Okay, so take note that this is one of the most important sketch you need to be familiar with. That's rate against concentration. Okay, rates against concentration. Make sure you are familiar with what kind of concentration you are dealing with. It could be the concentration of either of the reactant, and one of them must be in excess. Okay, so it is only when it is pseudo nth order that this kind of graph makes sense. Yeah. So for example, for the first column, right? If NO is not in excess, okay, definitely the rate of the reaction will not vary so nicely. Yeah, because if NO is not in excess, remember that it will be difficult to determine the rate, because the change in the rate of reaction as NO reacts, right, will also, or rather as oxygen reacts, will also be dependent on how much NO depletes over time. And because NO is not in excess, so it will deplete in a significant percentage, and this will cause the rates to maybe either drop or increase drastically depending on the actual order. Yeah, so it's therefore not so straightforward to study kinetics if one of the reactants in question has its order of reaction unknown, and then you kind of like make the stoichiometric ratio stoichiometric, and when they react, it's not very clear how they react. Yeah, okay, so in that case, as I mentioned earlier on, usually when people conduct experiment, they will make one of the reactant in excess, or some of the reactants in excess, or even the reactant, although it's not in excess, it's actually a catalyst. Yeah, so kinetics is actually a very, it's very tough discipline, and there are quite a number of variations. It's just that, number one, you need to be mathematically inclined to be able to derive some of the more advanced rate laws. And then number two is you need to have a more sophisticated understanding of some more advanced concept before you can appreciate further. Okay, I think at the H2 level, it will be suffice to understand whatever we have discussed. Okay, the next series of graph that is important will be concentration against time now. And as you are aware, the order of reaction with respect to oxygen is actually first order, and NO is in excess, right? So in this case, I'm going to expect a constant half-life. Sorry. Okay, so I'm going to expect a constant half-life, which will look like this. So it will be an exponential decay downwards. Sorry that I can't really sketch it very nicely over here. So yeah, it will be an exponential decay. So if this is A and this is A over 2 and this is A over 4, I'm going to expect the T half to be constant. So if that's it, this is T and this will be 2T. Yeah, so the T half is actually ln 2 over K prime. Remember that it's K prime, huh? It's K prime, huh? Not K. Okay, right? Yeah, so it's ln 2 over K prime, and then in this case, it will be a constant half-life. And then for the case of second order kinetics, we are really not quite interested in seeing how NO concentration varies with time, because again, you would expect the curve to be much sharper downwards. Okay, sorry, maybe not touching zero yet, much sharper downwards, or it will curve a lot more. And at the same time, the half-life is definitely not a constant. Okay, but based on what we would like to do in using mathematics, if we are going to plot rate against concentration squared, we're going to expect the straight line that passed through the origin. Okay, remember that this is concentration of NO raised to the power 2, so concentration of NO squared. Okay, so that's the difference. Okay, yep, right, so let us move on to question 1. Okay, so for question 1, we have an acidic medium where bromate, so this is known as bromate 5, it oxidizes bromide ions to bromine. So we have a series of experiments conducted involving different volumes of each of the reagents. So you have 1 mole per dNq of bromate, 1 mole per dNq of bromide, and 1 mole per dNq H+. You have a fixed volume of phenol being added to the mixture, and you were told that in the course of reaction, because you are producing bromine, the bromine will immediately react with the phenol to give you, in this case, you're not familiar yet, so let me just tell you, it will give you a white PPT lah. So in that case, the yellow-orange color of bromine will not appear. Okay, so the first instance for the appearance of the yellow-orange bromine, right? In that case, this will mean that appearance of yellow-orange, you will stop your stopwatch, and that is the time which you are measuring here. Okay, so this is known as a clock reaction. Okay, the only clock reaction which you are familiar with is what we call the iodine clock reaction. Okay, remember for iodine clock reaction, normally you will pour in an oxidizing agent, for example, S2O8 2-, which is colorless, and then you pour into another color solution, which is iodide. And then in the process, they actually produce iodine, but the iodine do not appear immediately because inside the solution, either iodide or peroxy disulfate, it also contains SO3 2-, known as thiosulfate, and this thiosulfate will react with iodine immediately. So the purpose of phenol in this experiment, right, is the same as the purpose of thiosulfate in the iodine clock reaction. Okay, it is used to react away the bromine that is being formed, so that you know that within that time frame, right, what is the fixed amount of bromine being produced within that time frame. Yeah, once you know the fixed volume fixed amount of iodine being produced, then you will be able to measure the average rate of production of bromine over that period of time. Yeah, so that makes a bit of sense lah. Okay, so I hope this explanation will help you to get a bit of sense of what exactly is going on in this whole business of the clock reaction. Okay, so these two columns, right, what you need to record here would be, first of all, you need to record 1/time, and it should be in the units of per second, and if possible, you should be able to measure the relative rates. Okay, so if you just quickly punch your calculators, you should be able to get 3.279 times 10 to the power minus 3, 1.299 times 10 to the power minus 2, 2.632 times 10 to the power minus 2, and 6.71 times 10 to the power minus 3. Yep. If you quickly take the relative rates, the smallest number is actually 3.279 times 10 to the power of minus 3. So this will be base to 1, and then after that, this is double of that, quadruples, and then this is 8 times. Okay, but before we proceed on, we need to be very clear about the total volume. You notice that for the first experiment, right, the total volume is actually twice that of the other experiments. So that means that in terms of the fairness in comparison, we shouldn't be comparing it directly. Okay, so in that case, we might want to rewrite the data for experiment 1, okay, over here, by basing it back to 1000. So when we base it back to 1000, all the values needs to be halved. So this is 250. This will be 300, this will be 400. Okay, yeah, but the time taken will still be the same because we are looking at the same bulk quantity. So this will still be 305, and then you will still base it to 1. Okay, then from here, I think it is relatively obvious how the order of reaction will appear. So okay, so the first thing we might want to do is let us just try to compare experiment maybe 2 and 4, because for experiment 2 and 4, right, you notice that the bromides and the H plus volume remains the same, okay, but the the volume of bromide doubles. So when the volume of bromide doubles, you notice that the relative rate doubles. Okay, so that will mean that it is directly proportional to the volume of bromides. So the rate of reaction is directly proportional to the volume of bromides. Some of you might ask at this stage, didn't we learn that we are looking at concentration doubling? How come we can look at volume? Aren't we taught that we shouldn't be looking at volume? Okay, now, because the total volume is kept a constant, right? So the change in the volume is a proxy to the change in the concentration as well. Okay? Of course, assuming that they are using it from the same source, and of course we are using the same source of bromide, H plus and bromine. Okay, so with that, if I'm not very clear what I'm talking about, you might want to revise your practicals, you might want to review a little bit of your notes. Okay, yeah, so therefore for bromides, it's actually first order. Okay, so this is first order. Right, then let us take a look at H plus. I think H plus, it will be good to compare 1 and 2. Yeah, so again, bromide constant, bromide constant, H plus volume doubles, you realize that the relative rate quadruples. Okay, so in that case, the order of reaction respect to H plus is 2. Okay, so using the same idea, we can compare between 2 and 3. So for 2 and 3, this is fixed. Bromide increase from 50 to 100. Relative rate doubles, so bromide is also first order. Okay, yeah, you can either solve this using mathematics. Okay, like for example, you let the rate law be you can let the rate law be rate is equals to K, then BRO3 minus M, BR minus N, and then H plus P, something like that. And then you divide the relative rate, and then you dump in all the values, and then you just cancel. Then you will be able to determine M, N, and P. Yeah, if not, you can write out verbally. Okay, in short proses, you can say that as the volume doubles, let's say between 2 and 4, the volume of bromide doubles from 125 to 250, while keeping the volume of bromide and H plus constant at 50 and 600 cubic centimeters. The relative rates double, so therefore it's first order. Okay, so all road leads to Rome, so there are quite a number of possible methods of doing. Okay, so this is one, this is 2. Okay, so this will be the rate law. Okay, it shouldn't be too difficult, so I hope everything else is okay. And then the last part will be state the units of K. I don't think this needs any further introduction. So usually in this case, we are looking at moles per dm cube because we are looking at a solution. So the units for rate will be moles per dm cube. Okay, and all these combined, it will be moles raised to the power of 3, dm, okay, sorry, not to the power of 3, but to the power of 4, and then dm to the power of minus 12. Okay, and then once we cancel it, let's look at both sides. So because k is here, right? Okay, so you just cancel this first, 3, and then you cancel this will be 9. Okay, so therefore the units of k, right, will be equals to mole to the power of minus 3, and then dm to the power of 9, and not to forget, I forgot to write it out here, the rate is per second, so that will be per second. Okay, so this will be the units for the rate constant. Okay. The next question 2, right? We are looking at a series of experiments being carried out to investigate the rate of reaction between H2O2 and I minus, depending on the concentration. Okay, so we have this, and then in the course of reaction, it leads to the production of iodine. Okay, and then H2O, they will mix together. So this is also some form of clock reaction. And then distilled water is added to make up total volume, and then the time taken for the color change due to the presence of indicator A. So in this case, you have an indicator A here. It's recorded. Okay, so you have several changes here. And then the easiest way to do this particular question is, of course, to plot a graph, because you notice that the concentration of H2O2 and H2SO4, they are all fixed. Okay, but you are changing the concentration of Ki, and then obviously in the course of reaction, the time taken changes, and of course the 1 over T being a proxy to the rate also changes. Yeah, so one of the common mistake is that students think that 1 over T is rates, but 1 over T is not rates, it's a proxy to the rates. Okay, because time is inversely proportional to rates. Okay, then from here, we'll just plot a graph. Of course, I won't be plotting it. It's because I plotted it for you already. So it's over here. So you realize that you get a straight line which passes through the origin. Okay, if you plot them out nicely, you get a nice straight line. And then from the plots, you're supposed to deduce the order of reaction with respect to iodides. Okay, so because it's a straight line which passes through the origin, so you expect the order of reaction to be 1. So it will be first order kinetics. Okay, and then given that the reaction is first order respect to H2O2, 0 order respect to acid, write the rate equation. Yeah, so therefore this will be quite straightforward. So rate is equals to rate constant K, Ki to the power 1, and then H2O2 to the power 1. Okay, so this will be a pretty straightforward question. Okay, yeah, we don't have a lot of kinetics question in our workshop here, so I think it will be good for you to revisit some of the questions in your tutorials, and as well as some of the past promo practices. Okay, so the next thing we are going to look at would be chemical equilibria. Okay, so normally for chemical equilibria, we recommend the use of the ICE table because it allows you to work things out systematically. Yeah, so although an ICE table is not 100% crucial, and most of the time marks will not be awarded unless say the equilibrium concentration or the equilibrium partial pressure or some of the important information is needed. Yeah, so most of the time the ICE table probably will not warrant any marks. As I said, there's a caveat to that, unless of course there are some information which requires from the ICE table. Yeah, but it will be a very good way of systematically deriving some of the data, and therefore and that is the reason why very often we advise the students to make use of the ICE table in their problem solving. Okay, so it will be extremely useful for you in JC2 as well when you are learning acid-base equilibrium, which proves to be one of the most difficult topic for your seniors in almost every other year. Okay, yep. So over here, what we are going to do is we're going to look at a guided exercise. So we have two gases, X and Y. They react in 2 dm³ reaction vessel. Yep. So we have 0.7 moles of X, 1.2 moles of Y present initially. When equilibrium was established, amount of Z was found to be 0.3 moles. So you are supposed to write the Kc expression for the reaction and state its units, and then after that hence show that the Kc value is actually 1.67. Okay, and then okay, so first of all, without going into too much details we need to first write out the Kc expression. Okay, so the Kc expression for this, it will be concentration of Z divided by concentration of X and concentration of Y. Okay, and remember that although it's not mentioned when we write this, just for the sake of simplicity, right? these are what we call equilibrium concentration. I think I need you to remember this. These are all equilibrium concentration. These are not initial concentration, okay? Yep. And because we are looking at concentration, so in order for us to derive the units, right? So that will be moles per dm cube divided by moles squared dm minus 6. So once we cancel the units, I'm going to get, this is minus 3 here, so I'm going to get mole to the power of minus 1 dm cube. Okay, so this is how we derive out the units. Okay, yep. So the first thing we need to do when we write out the ice table, right, is, okay, so it will be good again to write out the expression plus y g, okay, gaseous, equilibrate to give me z gaseous. Okay, so ice table, it is perfectly fine to write it as ICE. However, let us remind ourselves that we are looking at initial concentration and not initial number of moles. So we can write moles per dm cube over here. Okay, I think it is very useful for us to tell ourselves that we are looking at initial concentration. The reason is, I mean, it is also possible to work in terms of moles. It's perfectly fine, don't get me wrong. If you wish to, you can do that. Okay, but the reason why we prefer sometimes to work in terms of concentration is because, number one, we were told of the total volume. Number two, the individual amount is told to us. So because of that, why not just convert them to concentration, and we need to calculate Kc anyway, right? Yeah, so that's my rationale lah. Of course, as I said to you and you have seen in front, all road will lead to Rome. If you do it properly, of course, then it doesn't really matter how you choose to start working. Okay, yep. So in this case, the initial amount of X is therefore divided by 2, so you get 0.35 moles per dm cube. This will be 0.60 moles per dm cube. You do not have any Z at the start. Okay, you were told that the equilibrium amount of Z present is 0.3 moles, so you divide by 2, that will be 0.15. So if this is 0.15, therefore the change in the amount of Z is 0.15, and then this will be minus 0.15, this will be minus 0.15, you take the difference, you get 0.20 and 0.45. Okay, then from here, if you just carry on doing, your Kc would then be equilibrium concentration of Z, so that will be 0.15, divided by the equilibrium concentration of X, that will be 0.20, multiplied by the equilibrium concentration of Y, that will be 0.45. Okay, then when we punch our calculators, we should get 1.67 moles to the power minus 1 dm cube. Okay, yeah, so do get used to number one, construct the ice table, and number two, work on the problems in a systematic manner. Okay, I think if you are able to do that, then a lot of the questions can be easily solved. Okay, right? Yeah, I think over here the boxes are given for you to draft your ice table, which I have already done for you on the previous page lah. Okay, so if you wish to, you can just jot them down, or if not, then you try to attempt it in a separate piece of paper and then see how it goes along the way. I think that will help a lot. Okay, next let us move on to part B of this particular question. Okay, or it's a new question lah. Okay, so I have n moles of X is added to the vessel without changing the temperature. So a new equilibrium is established, and the new equilibrium concentration of Z was found to be 0.20 moles per dm cube. So let me just highlight this. Okay, it's 0.20 moles per dm cube, so that's for Z. And then calculate the value of N and the equilibrium concentration of X and Y. Okay, so this is quite an interesting problem. So let us go back to the original problem. So the original problem, right, you notice that the equilibrium concentration of X and Y has already been established. So that's 0.2, 0.45, and 0.15. So can we just write it out somewhere first to remind ourselves what we had earlier on? So this is 0.20. This is from the earlier equilibrium in blue. 0.45 and 0.15. Okay, so these are from the earlier equilibrium. Okay, then over here we were told that a certain amount of X was added. So in this case, I think for the purpose of clarity, you were told that let the change in amount of X be A. Okay, so in that case, this would then become 0.20 plus A. Okay, and then my Y will become 0.45, and then this will be 0.15. Okay, so I hope this is clear. And then you notice that from 0.15, my final amount 0.20, right? So there must be an increase in 0.05 for Z. If there's an increase in 0.05 for Z and they are in a 1:1 ratio, this must be minus 0.05 and X must be minus 0.05. And then eventually over here we'll get 0.15 plus A, and then over here we get 0.40. Okay, and remember that the question mentioned that this is being added without changing the temperature. Okay, very important, huh? Without changing the temperature. This is the super important parts. Yeah, because they did not change the temperature. Okay, so since the temperature is not being changed, okay, then what do we need to do? We don't have to do much. What we know is that equilibrium constant Kc is a temperature dependent variable. Okay, and because it's a temperature dependent variable, okay, what you're going to end up with is that you're going to write out the equilibrium expression again. So this will be 0.20 divided by 0.15 plus A. Okay, multiplied by 0.40. Okay, and then this whole thing will be equate to Kc, which is 1.67. Okay, then over here you solve for A. Okay, for A, then you should be able to get around 0.149 moles per dm cube. Okay, however, this is not the answer because this is not N. Why is this not N? Because the total volume of the vessel is over here, 2.0. Yeah, and because it's 2.0, right, therefore the value of N is equals to 0.149 times 2. Okay, so you should get 0.299 moles. Okay, so this will be the amount of X being added into the vessel. Okay, so take a while to think about the question, and then if there's any issues, you may go back to your notes and try to figure out a little bit, and then if you have other issues, can come back and watch this video again. Okay, next we'll move on to the question in the practice exercise. Okay, so for the first question, you are told that at a specified condition, 300 Kelvin and 1 atmosphere, N2O4 is 20% dissociated. So you are supposed to calculate the equilibrium constant in terms of partial pressure at 300 Kelvin. Okay, so what we are going to do here is just to write out in terms of ice table. So this will be N2O4 gaseous, equilibrate to give us 2NO2 gaseous, So I stable in terms of the amount. So we need to indicate it as MOL. Okay, so the initial amount of N2O4 will let it be X. So NO2 will be 0. Okay, because we were told that is 20% dissociated. So this will be minus 0.2 X, and then because of the stoichiometric ratio is 1:2 over here, so that means that in terms of X, this will be plus 0.4X. Okay, so the equilibrium amount would be 0.8X, and then NO2 will be 0.4X. So the total amount at equilibrium will be 0.8X plus 0.4X, that will be 1.2X. Okay, so because it's being maintained at 1 atmosphere, so therefore Kp in terms of partial pressure, that would be equals to the partial pressure of NO2 squared over the partial pressure of N2O4. So that will be 0.4x over 1.2x multiplied by 1. This whole thing squared divided by 0.8x over 1.2x multiplied by 1. Okay, so you would, after you punch your calculator, you will get the value 0.167 atmosphere. Okay, so this will be the Kp in terms of partial pressure. And then after that, you're supposed to calculate the degree of dissociation at 300 Kelvin and a total pressure of 0.2 atmosphere. Okay, yep. What you can take note of is that the temperature is the same, so therefore you would expect the Kp to be equals to 0.167 atmosphere. Okay, now so right now we need to recreate the ice table so that it will help us in our calculations. Okay, so I'm going to write it over here. So N2O4 gaseous equilibrate to give us NO2 gaseous, so this is 2. So in terms of amounts, ICE, okay, MOL, 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 okay. So because you are supposed to calculate the degree of dissociation, okay, so it will actually help if maybe you can let the initial amount again be X. Okay, so this should be 0. So the change is minus Y. So over here will be 2Y. So this will be X minus Y. This will be 2Y. Okay, so again, same narrative. So the total number of moles at equilibrium is equals to X plus Y. Okay, so that will be X minus Y plus 2Y. Okay, so same old story. So when you try to link it to Kp, so Kp will be equals to 2y over x plus y. This will be multiplied by 0.2. The whole thing squared divided by over here x minus y over x plus y multiplied by 0.2. So you equate the whole thing to 0.167. Okay, after that, we are going to simplify this to 4y squared, 0.2 squared divided by bracket x plus y squared over 0.2 x minus y over x plus y equals to 0.167. Okay, then we'll do some cancellation. Then let's cancel. This will cancel. Okay, and then we will bring the denominator over, so we'll end up with 0.8y squared equals to 0.167 x squared minus y squared. Okay, then we'll just bring the terms together. We'll get 0.967 y squared equals to 0.167 x squared. Okay, then we'll express y in terms of x, so y is actually equals to 0.416x. Okay, then we are supposed to determine the degree of dissociation, right? So therefore the degree of dissociation will then be equals to y over x. So this would be equals to y in terms of x is 0.416. So that will be 0.416x over x. So you end up with 0.416. Okay, so this will be your answer to part B. Okay, and then next you are supposed to calculate the pressure that must be applied so that the degree of dissociation is lowered to 15%. Okay, so with that, I think we'll go through the same thought processes. So before that, I'm just going to erase most of this thing because they are probably not entirely needed. Okay, so I'm just going to erase all this. Okay, in order to simplify matters a little bit. Okay, again, we will work in terms of x. So earlier on, it's mentioned here that the degree of dissociation is lowered to 15%, right? So this will be minus 0.15x. So you expect this to be 0.3x. Okay, so equilibrium amount will be 0.85x. So this will be 0.3x. Okay, so the equilibrium total number of moles would then be equals to 0.85x plus 0.3x, that would be 1.15x. Okay, so because it's at the same temperature, so Kp will be constant at 0.167. Again, you will equate this to 0.3x over 1.15x multiplied by the total pressure. Okay, because the question asks you what is the pressure that must be applied. Okay, so you let the pressure to be applied be P total, and then after that this will be 0.85x over 1.15x. Okay, and then you solve for this, you should get total pressure after punching calculator to be 1.81 atmosphere. Okay, next we are going to look at question 2. Okay, so for question 2, you are told that you are given a 1:3 molar ratio of nitrogen to hydrogen, and they were mixed together in a container of fixed volume at 350 degrees Celsius. And then, of course, the following equilibrium was established. And the partial pressure of hydrogen was found to be 28.0 atmosphere at equilibrium. Yep, so for part A is a very standard question. I'm sure you do anticipate that. So they are asking you to write out the Kp expression in terms of partial pressure. So that would be Kp is equals to the partial pressure of NH3 squared over partial pressure of N2 multiplied by the partial pressure of H2 cubed. And then I'm supposed to give the units, so that would be atmosphere squared divided by atmosphere to the power of 4, so therefore the units will be atmosphere to the power of minus 2. Okay, so for part B, you were told that the value of Kp was found to be 7.69 times 10 to the power minus 4 at 350 degrees Celsius. So we better check that the temperature is the same. Okay, so 350, 350. Okay, so this is the value which we need to work with. And then you are supposed to calculate the partial pressure of nitrogen and ammonia at equilibrium. Okay, so let us try to do it. Okay, so again, we are going to construct the ice table. So I'm going to write out N2 gaseous plus 3H2 2 gaseous equilibrates to give us 2 ammonia gaseous. Okay, and then I'm going to write out the ICE table, ICE. Okay, but in this case, I'm going to work in terms of partial pressure. Why is that the case? Because I'm given the partial pressure of hydrogen at equilibrium, which is given to be 28 atmosphere. Yeah, so in that case, based on this fact, it might be easier to work in terms of partial pressure. Okay, when you are not sure, you should always try first. Okay, so like during non-assessment times, you just try using even if you want to number of moles, but you realize that you'll be stuck somewhere. Okay, so with that, let us try using atmosphere. Okay, so initial will be ATM. Okay, so I'll just write the units. Usually when you write out the units, it will remind you what you are dealing with. So if you are dealing with number of moles, I think you should write out the units as moles. If it's in concentration, it should be in moles per dm cube. Partial pressure, then either atmosphere or Pascal. I mean, usually kilopascal. Okay, so you were told that the initial ratio is 1:3. So this is a very big clue. Okay, so let us assume that initially you don't know how much N2 you have. Please note that you cannot write it as 1:3, because they did not tell you that you begin with partial pressure of 1 atmosphere. So you shouldn't write it as 1:3. So in this case, you should write it as X and 3X. Okay, and then initial partial pressure of ammonia is 0 because you are not forming ammonia yet. And then the change in this case will be minus Y, and then minus 3Y, and then plus 2Y. Okay, and then the equilibrium partial pressure of nitrogen would be X minus Y, and then for hydrogen will be 3 bracket X minus Y, and then of course ammonia would be 2Y. Okay, and the clue you were told over here in terms of the information given to you is that the partial pressure of hydrogen was found to be 28, and then the Kp value was this. Okay, so this is a very big clue because with that particular clue, right, we know that 3 bracket X minus Y equals to 28. Yeah. So therefore, in this case, X minus Y would be equals to 28 over 3, which is equals to 9.33 atmosphere. So this would be the equilibrium partial pressure of N2. Okay, and of course, the one given here is actually the equilibrium partial pressure of H2. Okay, H2. So this is at equilibrium, and this is at equilibrium. Okay, and then from here, let us try to use the Kp value to solve. So in this case, Kp is given to be 7.69 times 10 to the power minus 4. I'm going to write out the Kp expression, so that will be 2y squared over, in this case will be X minus Y, but we do know what is X minus Y. So X minus Y is actually 9.33. Okay, and then we do know the equilibrium partial pressure of hydrogen, that is 28, so 28 cubed. Okay, and then from here you actually don't need to solve for Y. Okay, why is that the case? Because you are supposed to find out the partial pressure of nitrogen and ammonia at equilibrium. So we have already found out the partial pressure of nitrogen, which is 9.33. So the next thing we want to find out is the partial pressure of ammonia in terms of 2y. We don't have to actually change anything. Okay, so from here, you will solve, and then you will get the partial pressure of ammonia, which is equals to 2y, and if you just punch your calculator, you should get 12.6 atmosphere. Okay, so please try to work it out on your own and see whether you can get the answers. Okay, then the final part is actually part C. Calculate the percentage yield of ammonia at 350 degrees Celsius. Okay, so now they want the percentage yield. Okay, what will we do in this case? Okay, we will now look at, let's say if the reaction were to go to completion. Okay, so if the reaction were to go to completion, I'm going to get the maximum amount of ammonia, and this is actually dependent on X and 3X. Why is that the case? Because they react in a stoichiometric ratio. Yeah, so I can either look at X or 3X, but I think it's easier to look in terms of nitrogen. Yeah, because the ratio of N to ammonia is 1:2. So therefore, in a relatively simplistic manner, the percentage yield of ammonia, right, is simply just 2y over 2x. So it's basically a y is to x ratio, if you want to put it that way lah. Yeah, because 2x is the maximum amount of ammonia you can achieve. Okay, so in this case, since we already know 2y, we can easily, I hope you do recognize it, we can easily solve for x. Okay, whichever equation you want to use, so maybe we can use it from here. So in that case, I'm going to get x minus 12.55. Why 12.55? Because that is the actual value of the partial pressure ammonia, but we just round up to 3SF over here. So divide by 2, and this is actually equals to 28.3. It's simply based on this equation. And then we will calculate X to be around 15.61 atmosphere. Okay, so if X is 15.61, then that means that 2x will be just double of this, so we can easily get 31.22 APM. Yeah, of course we can also solve in terms of simply just y over x lah, because the 2 cancel out. But I mean, if you want to, you can do that. But in this case, I would prefer to just use 2x for simplicity. Okay, so from here onwards, we are going to get our 2y is 12.55. It's a full value, and then divide by 31.22, and then times 100%, and then eventually I will be able to get 40.2%. So this will be the percentage yield of ammonia. All right. Yep. So for those of you who actually prefer to work in terms of simply y and x, then you can simply just do the same thing. So you can simply just take 12.55 divided by 2, which gives you the value of y, and then divide by 15.61 times 100%. So you should be able to get 40.2% as well, because 12.55 divided by 2 is about 6-ish. 6+%, and 6 plus atmosphere, and 6 plus divided by 15.61, that's also about 40-ish%. Yeah, so the answers will be the same. Okay, so I hope you're not confused. If you're confused, just go back and think about how to go about doing it. And yep, I hope you'll find the video fruitful and helpful towards your learning.